Okay, so here let's see how we can derive the E field generated by this dipole along the dipole axis. Okay, so here we have only two charges, so we only need to calculate the E field generated by each of them one by one. So the total E field is actually E plus, which is the E field generated by the positive charge, and then minus the E field generated by the negative charge. Okay, so originally it should be adding them together, but as much as we know, okay, so for the positive charge, it will generate E field pointed away from it. So at this point P, E plus should be pointing upward, and then for the E minus, okay, this is a negative charge. So the E field should be pointing towards this negative charge. So at this point P, the E minus should be pointing downward. Okay, so in such a way, we also know that E plus should be slightly larger than E minus. Okay, so we will use E plus minus E minus. Okay, so here we just need to use the original equation. So here we have K times Q, and then R plus square, and then similarly E minus will be K times Q, and then R minus square. Okay, so both of them has the same charge magnitude but with opposite direction. So here we only use Q for them. And then R plus and R minus are a little bit different. Okay, so here you can see R plus is actually here. R plus is actually here, starting from this positive charge to the point P, and then R minus is starting from the negative charge to the point P. And then also for the Z here is actually starting from the middle point of the dipole to the point P. Okay, so here we have 1, 2, 3, 4 different distance. Okay, actually the D is the distance between these two charged particles. Okay, so here we try to replace actually we try to express R plus R minus using Z and D. Z and D are considered to be known value, and then R plus R minus are some dependent variable. So here we will try to use Z instead of R plus R minus. Okay, so in such a way, it is a very simple geometry problem. So here Z will be, or I should say, R plus should be Z minus half of D. Okay, Z minus half of D will be R plus, and then Z plus half of D will be R minus. Okay, so it is very simple according to this figure. And actually KQ are some common factor, so we just put them out. Okay, so the remaining fractions in between, so this is the difference of this fraction and this fraction. Okay, so in that case we also try to factor out a z square, so that we would try to make this a 1. Okay, make this a 1 so that we can do some expansion. Or maybe you can simply do some approximation. So here we try to factor out a z. Okay, so of course this is a square, so it turns out to be a c square here. So in such a way we actually make it like over z square, but in this parenthesis we try to divide by c. It by c. Okay, so here z over z will be 1, and then here we have dE over 2z, and then here we have 1 plus d over 2c, something like this. So far we doesn't do any approximation. It's only some simple algebra. Okay, so here we try to subtract them. Okay, so by multiplying the common factor, so the denominator becomes something like this, which is this one multiplied by this one, and then the numerator will be this one subtracted by this one. Okay, so this is a perfect square, will be a squared plus 2ab minus plus b squared, and then this one will be a squared minus 2ab plus b squared, something like this. So subtracting this one by that one will be 4ab. 4ab will be 4 times, okay, will be 1 plus d over 2z square minus 1 minus d over 2c square will be 4 times a times b, something like this. Okay, so 2 and 4 will be partly cancelled, will become a 2d over z. Okay, will be 2d over z will be here. Okay, so other thing doesn't change at all. So here is the common denominator. Okay, so so here we try to do some approximation. So here we try to assume that z is much larger than d. Z is much larger than d. Okay, so in such a way, z is much larger than d, which means that this fraction will tend to 0. Okay, will tend to 0 if z is much larger than d. Similar for this one. Okay, so this one become a 1, this one become another 1. So all the denominator becomes nothing but a 1. So finally it becomes so this one becomes a 1, this one also becomes a 1. Okay, so finally it becomes kq over z squared times 2d over z. Okay, something like this. So finally it becomes k times 2qd over c cubed, something like this. And then qd is actually the p, the electric dipole moment. So finally it becomes something like this, k times 2p over c cubed. K, this is k times 2p over c cubed. Here only write it as a vector form. Okay, so any question for this derivation? Okay, so for this assumption, z is much larger than d, sometimes we can call it a far field. far field， far field， 中文叫做远长。far field。因为远的话，通常就可以做一些简化，而且它原来的话通常会比较规律。那近的话就是会比较乱一些，比较没有那个规律，所以就没有办法，就是如果没有这个近似的话，那个式子就会看起来像上面那个看起来就会复杂很多。但是如果假设了 c 远大于 d 之后，这剩下一个比较简单的结果。Okay, so next we try to consider a more complicated case. So here we try to consider E field due to a line of charge. 这是一个圈的电荷一个圈的电荷。So here the different thing is that the equation for E field set up by a particle does not apply to an extended object with charge. Okay, so it means it has a continuous charge distribution. 就是有一个连续的电荷分布连续的电荷分布。因为前面说的是如果我们是一个一个电子一个一个电荷的话，那你算电长的话，就一个一个算完就加起来就好嘛。但是现在是连续的，那你怎么数出来怎么把它分成一个一个小电荷呢？所以这是另外一个问题。Okay, so here is to find the electric field of an extended object at the point we first consider the electric field set up by a charged element in the object. 就是我们先把这个连续的分布把它切成一小块一小块 ，a charge element called DQ 啊，就是微积分嘛，微积分就是d 什么 d 什么嘛，啊，那我就有一整圈都是电荷，那我就把它切成一小个一小个 DQ 啊，每个小个的 DQ 我就可以把它当成一个 charge particle， 然后就去用那个E 的公式啊。对于一个电荷的公式去算啊，算完之后我们把所有的加起来 ，OK，where the element is small enough for us to apply the equation for a particle, then we sum via integration。那切完之后我们要加，怎么加？因为本来是连续的，那如果你把它切得很小很小的话，那它就会有无穷多个啊。那无穷多个要加的话，它就是一个积分，就是类似那个黎曼河的那种感觉啊。So components of the E field dE from all the charges element，OK，就是说我们把它切成很多个 DQ 之后，那每个 DQ 算出来的就是一个 dE， 就是一个小电场啊。所有小电场我们再用方式把它加起来啊，就是用个积分把它积起来，那就变成一个大的整个的电场。So a ring of uniform positive charge, a differential element of charge occupies a length ds. Greatly greatly exaggerate for clarity， 就是它是夸张的，就是因为它本来说 dq 应该要很小嘛，所以这个 ds 应该也很小才对，但是它画的很小，你又看不到，所以的话就是画的比较长的，你就想象它很小就好了。Okay, so this element set up an electric field dE at point P. Okay, so here we consider a line of charge, or actually a ring, a charge ring, 就是一个带电荷的一个环一个圆环。然后我们要算的是这个电场，那跟前面那个类似，我们没有办法算整个空间任何位置的电场。那我们只能够算出来这个轴上面，那这个轴跟前面的定义有点不一样，这个是一个圆嘛，所以我们这个轴的定义是这个圆的圆心就通过这个轴，但是这个轴的话是垂直这个圆圈垂直这个圆圈的面所以这个 z 轴是这么定义的。那随便定义哪一个正哪一个负都无所谓它后面有个平方的，所以正负都一样。Okay, so actually this is a charge ring, or actually a circle. So we try to separate this ring into many small parts. Each part the length is ds, and then within this ds we assume it is very small, and then the charge on it will be dq. The overall charge of the whole ring is q, but the dq is actually the charge within this ds. Okay, and then we assume this dq is a charge particle, so that we can try to calculate the dE generated by this dq at point P, and then we try to repeat it for different segments, and then we try to add them together using some mathematical method. Okay, so the idea is something like this. So here, the first step is to cancel the components. Okay, so using this method will be very tedious. Okay, you need to do some integration. But as much as it can use the hand calculation, so it has some symmetry, 就是有一些对称性it has some symmetry, so that some of the component can be cancelled. Some of the component can be cancelled, so that so usually you only need to compute the E field along a single axis. Along a single axis, 就是因为本来的话是很多dE都是向量，那每个dE都指不同的方向，那又要分量，那就很麻烦嘛。所以它通常有一些对称性让它某一些方向是可以抵消掉，那只剩下某一些方向要算的。所以第一步的话，我们就先知道那个方向，然后去看看 哪一个分量是可以抵消的。So cancelling components it will be the following step. So the charge element on the opposite side of the ring, they contribute the field dE, but the field vector leans at angle theta in the opposite direction from the vector of our first charge element. Okay, so the idea is like, of course, we need to separate into ds and then calculate dE one by one, but there are some symmetry. So we can, for a circle, for a perfect circle, you can also find the symmetrical part. You can also find the symmetrical part. Okay, so this maybe we can call it d or ds prime or ds if you like. So let's say this is ds prime. So ds prime will also generate the E field at point P somewhere like this. Okay, maybe we can call it dE or dE prime. In this textbook, it just call it dE, and then this one is only ds. But the idea, yes, so it doesn't really matter. So suppose this ds is generating dE here, and then this is the cross section. The cross section, so actually you assume this orange one is this one, and then for the ds prime is generate a dE prime is actually this one, Okay, as it mentioned, the angle is theta, not a vector. The angle between this dE and dE prime to the z-axis is theta. Okay, and then actually we already find ds and ds prime are already symmetry to each other, so that this component will cancel each other. Okay, I mean this component and this component will cancel each other. So yeah, I cannot say whether it is x-axis or y-axis, because if you go along the circle, okay, it may move from x-axis to y-axis or somewhere between. So yeah, so we can only say that the component here, a horizontal component, will cancel each other. Only the vertical component will superimpose. So the vertical component of them will be dE times cosine of theta, because theta is here, so this one will be a dE cosine of theta for each of them. Okay, we don't try to put a 2 here. We will still integrating over the whole circle, so that we just make them as dE cosine of theta. We only know that, okay, we only need to know that the component, the z-axis component of dE will be dE times cosine of theta. Okay, so on the next page, we will try to calculate the dE generated by the whole ring by the integration. So in the previous page, we already know that the magnitude of dE of the for the uncancelled component of dE will be dE times cosine of theta, dE cosine of theta. And here we try to find the expression of cosine of theta so that we can do the integration. So actually theta is here, and then theta is also here. Okay, as much as this is a straight line, this is a straight line. Okay, so and here, okay, this one is z, this one is z, and then this radius of the ring should also be a known variable, and then the z should also be a known variable. The only unknown variable will be here, will be the r, okay? But actually, the cosine of theta is actually z over r. Cosine of theta is actually z over r. So we would like to express r in terms of z and capital R. So according to Pythagorean theorem, r will be the square root of z squared plus capital R squared, will be like this. Or we can actually write it as z over these things, z squared plus capital R squared. and then the whole 1/2 power. Okay, so this is the expression of cosine of theta. So dE will be something like this. dE will be something like this. Okay, I mean dE cosine of theta will be something like this. Cosine of theta is this one. So we put it here, and dE. Okay, so here we have dE. Actually, for dE, you will consider it is dE to be k times dq over this r squared, something like this. Okay, but here we don't know what is dq. Okay, here we will also introduce another variable called the linear charge density. Okay, using the Greek letter lambda to represent this linear charge density, and the SI unit of this linear charge density will be C over M. C over M. C is the total charge. It's the charge. It's the SI unit of charge. So it's C here over M. Over M. So the coulomb for each meter. For each meter. So so this is a linear charge density. So what is this lambda? Okay, actually the lambda is like 就是这个密度嘛，这种密度的意思就是说它的电荷 dq would be lambda times ds。 OK， 这个是长度，这个是长度的线性的电荷密度。那长度乘完这个每长度的电荷量的话，乘完之后就是电荷量嘛。所以就是 dq 等于这个 lambda 乘以 ds， 所以我们就把这个 lambda ds 放在这个位置放在这个位置So here actually k is actually this one 1 over 4 pi epsilon naught, and then we have a dq to be this lambda ds, and then we have r square, and similarly r square should be z square plus capital R square. Okay, and then this one combining with this one. Okay, this is first power, and then this is a half power. So all together become 3 over 2 power. 3 over 2 power. And actually, we try to somehow collect the terms. So 1 over 4 pi epsilon naught here is here. And then c times lambda, we put it here, ds putting to the back, and then these two combine to be z squared plus capital R squared to 3 over 2 power. So this is the expression of dE times cosine theta, and then this expression it is ready to be integrated. It is ready to be integrated. Okay, so here we try to do the final step is the integration. We already come up with the expression of the effective component, and then we try to integrate it over the whole structure. Okay, in this structure is a circle. So for this one, the ds is the length of the circle. So this ds will be nothing but 0 to 2 pi r. 0 to 2 pi r. And actually, you may ask, why do you need integration? Because you are integrating ds, and then this whole thing is independent to s. Okay, it's independent to s. So it is just like integrating a constant. 就是你在积分一个常数，其实你根本就不需要积分。那其实这个意思是让你在这个例子当中熟悉这个积分怎么用那后面的话真的要用的时候你就会用上。那如果现在我就很简单的用一个乘法去代替的话，那就没有一个你看一个积分的一个例子就是让你多一个例子使用到这个积分，虽然它只是一个积分一个常数，那就很简单，积分一个常数就是一个乘法。Okay, so it will be something like that. Okay, so we try to integrating this dE cosine theta along the whole length, and then this length for a circle is nothing but 2 pi r. So we integrate from 0 to 2 pi r, and then this whole big rectangle is a constant. So we can just put it out and then integrating 0 to 2 pi r ds will be nothing but 2 pi r. Okay, so it's something like that. So we put this thing in the front and then multiply by 2 pi r. It is nothing but that. So finally, we can just combine something back. So we can actually eliminate this lambda because this lambda is what we assume in between. It is not a known value. So actually for the lambda, it is actually related to Q over 2 pi r will be this lambda. Okay, so according to the linear charge density, of course the charge is uniformly distributed. So the density will be a constant over the whole ring, and Q is the total charge on the ring, and then the 2 pi r is the length of this ring. So Q over 2 pi r will be the linear charge density, will be the uniform linear charge density of this ring. Okay, so finally we can actually eliminate the lambda by, okay, we can slightly move a bit so that Q equals 2 pi r lambda. Okay, we can replace it by Q. So actually we can observe that this is this is lambda, this is 2 pi r. So this 4 variable becomes a Q. So finally here become a Q multiplied by Z here. And then 1 over 4 pi epsilon naught is nothing here, it's nothing but that. And then this one is also similar, putting it here. Okay, so this is actually the closed form solution for the E field along this z-axis. Just introduce. And okay, so here the charge ring will have an E field, something like this. And here we also try to assume that Z is much larger than R. Z is much larger than R. So this R is the radius, of the ring. Radius of the ring 就是那个环的半径，环的半径。然后我们也假设这个距离距离的话就是这个点到这个环的圆心的距离，就是 z 的话就是远大于这个半径，就是也是一个 far field 的 assumption far field 的 assumption 一个远长。Okay, so here if we assume z is much larger than r, this expression can also be simplified. So the simplification is something like here in this parenthesis we have z squared plus r squared, and if z is much larger than r, then in that case we can ignore this r squared. So finally it turns out to be z squared and then 3 over 2 power. So which means that this whole thing is approximate to z cubed. Okay, so here we have z cubed and then partially cancel with this z, so becomes a z squared. So finally it becomes a very elegant expression like E equals 1 over 4 pi epsilon naught Q over C squared. Okay, it's similar to the E field generated by a charged particle. And actually the point here is to say that is if you consider the E field generated by this ring along this axis, if this point is far enough, you can also consider all the charge are all concentrated at the center. 就是如果你是现在有一个圆环，它有一个均匀的联合分布，然后你现在要算这个圆环的轴就是垂直这个圆的面，然后通过这个圆心的这个轴然后如果你考虑跟点很远的话，它就相当于所有的电荷都集中在圆心，是一样的，就是通过这个 approximation 我们就是看到这个式子长这样，就是它跟一个电荷产生的电场是有一个一样的一个公式。Okay, so far any questions? 有没有问题？可以用中文问。Okay, if no question, we move on. So here with a sample problem. So in that case, yeah, so we will do some integration. Okay, so here let's see. A plastic rod have a uniform distributed charge negative Q. The rod has been bent in a 120-degree circular arc of radius r. OK， 现在我们有一根杆子啊，杆子是把它掰成一个圆弧啊，120度的圆弧，然后半径它的半径曲率半径是小 r. Okay, we place coordinate axis such that the axis of symmetry of the rod lies along the x-axis, and then the origin is at the center of the curvature P of the rod. 所以它的意思是我们这个坐标轴的原点在这个圆心的位置，然后它在这个圆弧的中间，所以上面60度，下面60度，就是大概是这个意思。And then in terms of Q, in terms of capital Q and R, okay, in terms of capital Q and R, what is the electric field E to the rod at the point P? Okay, also calculate the E field at the center. Okay, and actually the charge is negative Q rather than Q. Okay, so yeah, so actually for this figure we try to cut it into small segment. So like this one will be ds, okay, and then also we can find the symmetry part ds prime, okay, which is symmetry to the x-axis, so that ds will generate de, okay, and then actually this is a negative charge, so all the small segment will also be small negative charge. In that case, DE will be pointing to that segment, which is the top right direction. Okay, so this is DE, and then similarly for DS prime, the DE prime will be pointing to the bottom right. Okay, so as much as they are symmetry, so in that case, the y-axis will cancel each other, so only the x-axis component will be superimposed. Okay, so here we will have quickly determine that the EY, which means the y-axis, are cancelled. And then DEX are summed. Are summed. Okay. So actually, DE is actually 1/4 pi epsilon naught times. Similarly, we have a lambda ds, okay, over r square. R is the radius, and then lambda ds. Lambda ds is also the dq. Okay, it's also the dq. So it is the lambda is the line charge density. And similarly, we will have lambda to be positive or negative. We can simply consider it is a positive value. So Q over 2 pi r, and then it is not a full circle, it's only 120 degrees, so it is 1/3 of a full circle. So we will have lambda to be Q over 2 pi r, and then times 1/3. Something like this. So and then according to what we argued just now, dy cancel each other, and then we only need to calculate dex. So dEx will be dE times cosine of theta. Okay, this is theta. Okay, so dEx will be dE times cosine of theta. So here we have dE to be this one. dE is 1 over 4 pi epsilon naught times lambda ds over r squared. Okay, so this is nothing but dE, and then we have cosine of theta. Okay, here actually we have the theta here, so we cannot simply use the ds to integrate. Here we need to use another substitution. Actually is the polar coordinate. Polar coordinate 就是这个叫做极坐标啊，极坐标。看极坐标，极坐标的话是说。我们有一个坐标系嘛，就是某一个点的话，我们就用一个半径啊，一个距离跟一个角度，从 x 轴开始算的一个角度去算。那如果我们有一个 ds 的话那这个 ds 的话就会等于这个 r 乘以 d theta 啊，这里叫做 d theta， 就是一个圆弧啊，圆弧的话就等于半径乘那个角度嘛。但这个角度的话就是要是 radian 的，你不可以是度数的，那就会满足这个 ds 等于 r d theta。所以我们做这个变数变换。So with this substitution of variable, we have 1 over 4 pi epsilon naught times lambda, and then ds will be this one, r d theta, and then over r squared, and then cosine of theta. So here r and r squared can be partly cancelled, and then so finally it becomes 1 over 4 pi epsilon naught, and then lambda d theta over r, and then cosine of theta. Okay, so we stop here, and then we can start to do the integration, so that in the previous page we stop here, and then finally we should calculate E to be the integration of dEx over this L. This L is assumed to be this rod, to be the L. Okay, so we try to put this expression here, 1 over 4 pi epsilon naught, and then times lambda d theta r squared cosine of theta. This is just what we evaluate. So we just use this to replace it here. And of course, this is a finite integral, so we need to define the lower bound and the upper bound of this finite integral. So actually, just now we mentioned that this is actually negative 60 degree to positive 60 degree. Okay, the theta here is starting from the x-axis, so it's from negative 60 degree to positive 60 degree, but we should use a radian. So in that case, it should be negative pi over 3 to positive pi over 3. So actually this one is negative 60 degree, but we should use a radian. Okay, so you can do the integration, but first we can just put out all the constant terms which are independent to the theta, because we are doing the with respect to the variable theta. Okay, so actually 1 over 4 pi epsilon naught is independent to theta, and then lambda is independent. R squared is also independent. So the only remaining variable is cosine of theta, b theta, and then from negative pi over 3 to pi over 3. Okay, so this one is easy to integrate. The antiderivative of the cosine of theta is sine of theta. So it is nothing but 1 over 4 pi epsilon naught times lambda over r squared. And then we have sine of theta evaluate from negative pi over 3 to pi over 3. Okay, so here we only need to substitute pi over 3 to here, and then minus sine of negative pi over 3. Okay, so sine of pi over 3, sine of 60 degrees is square root of 3 over 2. And then sine of negative 60 degrees is negative square root of 3 over 2. So this thing becomes a square root of 3, right? So it turns out to be square root of 3 over 4 pi epsilon naught times lambda over r squared. And then finally, we need to use this one. Lambda equals q over 2 pi r over times 1 over 3, which is like lambda equals q over 2 pi r times 1/3. Okay, and then we try to substitute this thing into here. Okay, so it turns out to be something like 0.83 over 4 pi epsilon naught times capital Q over r squared. The expression will be something like that. Okay, so this will be the expression of the E field generated at the center point, which is the point P. And of course, it will be smaller than the previous case. Smaller than the previous case because we only have a arc of 120 degree. Yeah, but it's not that small yet, because if it's a through ring for the center point, all the E field will be cancelled. So yeah, so at least for this case it is a 120 degree arc, but yeah, the magnitude of the E field at the center point will be something like this. Okay, so any questions? If no questions,